Hey there. How are you?
Hey, good. How's it going? You can hear me okay? Or oh wait,
I
yeah. Oh,
can.
you can. Okay. Okay. Perfect. All right. Sorry.
Awesome. So yeah, what's new?
I finished the Jack Weston diagnostic.
Okay.
Um, yeah. So just kind of been focusing on that pretty much, just trying to get through that, and then yeah, yeah. So those are kind of the.
Hmm.
It doesn't really tell you.
You go to the details.
Okay. Okay.
So have you reviewed these yet?
No. I think you might have mentioned like kind of narrow like filtering them out the ones that really that's what okay. I knew I was missing something. Okay.
Sure. So let's go over some of the questions that you have from this stuff.
Okay. Um where's my I did flag some down, but I flagged some down in the chemistry, so I was more diligent about that, but I didn't flag them out in the biochem. Should we start with the chemistry or just start with biochem or does it matter?
Sorry, you said that you already had questions lined up for chemistry?
Yes, yes.
Yep.
I just
Mm-hmm.
yeah, yeah, I forgot to do it for
Yep,
I
that's fine.
forgot to do it
Mm-hmm.
for biochem. So I guess I'll have to go some other time. And, let's see here. Test. Just trying to pull up. I put it in the. Sorry, I'm just trying to find that sheet. Perfect. Okay. Number 10. Yes.
All right. So, um, okay. So yeah, how would you approach this?
Let's see here. So I'd start with what I'm given, 2.25 moles nitrogen gas, and recognizing that that's referring to this right here, and I'm recognizing the ratio
Nope.
that there's. Oh,
What's that?
oh, sorry. I'm sorry. This one here.
Okay,
Yeah.
yeah.
Sorry. I'm sorry about that. Yeah. So
Yep.
the three. So I'm starting with what I'm given, the 2.25 moles, and the ratio is three. And then it's asking how many grams of sodium azide,
Yeah.
which is this right here. So it looks
Okay.
like a 3-to-2 ratio.
Uh-huh. Uh-huh. Yep.
So I'm going to do some type of stoichiometry to integrate um, the ratio and utilizing the moles, calculating the moles of nitrogen gas, which I
So we're given the moles of nitrogen gas, right? And then the chemical reaction, the balance reaction here, shows us for each mole of nitrogen gas, or for each 3 moles of nitrogen gas, you get 2 moles of sodium azide. So we can use that to figure out how many moles of sodium azide you get if you had started with 2.25 moles of nitrogen gas. So then we're going to find out the moles of sodium azide, and then we just use the gram formula mass of sodium azide to figure out how many grams that would be. So, so basically, we can do this. We could do 2.25 moles of N2 gas, and then we can write that, like, whatever the mole kind of ratio here. So for each or rather, for each 3 moles of N2 gas, we should have 2 moles of sodium azide, right? Then So that'll give us the moles of sodium azide, but we want the mass of sodium azide. So we can use the gram formula mass then, right? Or the molecular mass, right? For
Yeah.
1 mole of NaN3. So let's look at the periodic table here. So Na is 23, and it was Na and what was it? It was NaN3, and
Yeah, NaN3. Yeah.
then nitrogen
So
is 14. So 14 times 3. So I mean 15 times 3 would be 45, minus 3 would be, 42. But so 42. So this is 66. Um
65 or yeah.
oh yeah, 65.
Oh,
Yep.
sorry.
So 65 grams of sodium azide in 1 mole of sodium azide. And then this will give us our answer in grams of sodium azide.
So I guess where I messed up was
Mhm.
I plugged in. I did I did over here 1 mole of N2, and then I over 28.
Oh, you
Um,
did the molar mass of N2.
yeah, of nitrogen. So I did 14 times 2, 28, and so I guess that
So,
wouldn't make sense because they're not. Yeah.
so yeah, so we want to think about it like this, right? The so if they're giving us the moles of nitrogen gas, right? We use this balance reaction to figure out how many moles of sodium azide we get. So then we take the moles of sodium azide that we're supposed to get, and we use the gram formula mass to figure out the grams of sodium azide. But we didn't need to do that to find the grams of nitrogen gas because they are already giving us the moles of nitrogen gas, and we know from the balanced equation that if we have, you know, moles of nitrogen gas, we would be able to figure out how many moles of sodium azide we would get, right?
Yeah, it makes sense what you're saying now, but I guess like my brain went to autopilot. Like, oh, I saw the moles. I need to like do stoichiometry and just kind of cancel it out.
So let's say instead of 2.25 moles, right? Let's say we had 45 grams of nitrogen gas, right? Then you would do like 45 grams of N2 gas multiplied by, so N2 gas is what is it? 28.
Yeah.
28 grams in 1 mole of nitrogen gas, and then you would use the, you know, 3 moles of N2 gas for 2 moles of NaN3, and then, the rest of them
Okay.
after that. So if they gave you a mass of nitrogen gas, then you would convert that into moles because you need to in order to use the balanced reaction.
Okay. Okay. That makes sense. Hello.
Oh, hey.
14. Yeah, 14.
Mhm. So, yeah, what what were your thoughts here?
Um, so this seemed
Yeah,
like an
exactly.
ice chart maybe, or like a plus X minus X type of thing going on. Um,
Okay. So, um, so anything that has a capital K.
Uh-huh.
So,
Okay.
is that someone on your end or?
sorry. Oh, it's just a cubicle behind me. I apologize.
Got it, got it. Got
Sorry
it.
about that. Yeah.
So, okay, any K, so like K E Q, K W, K A, K
Right. Because when we checked, you couldn't hear anything, right?
A,
It wasn't
B,
making a noise. I mean, I was there also. We couldn't hear it,
all
right?
of that
So,
stuff
yeah.
is derived from something called the law of mass action, which is essentially just uh like products over reactants, right? If you had like, this reaction, let's say, with the capital letters being the identity of the molecule, and the lowercase ones are just their coefficients, right? Then you would do product, so B to the lowercase b power, C to the C power
Yeah.
over
Yeah.
A to the lowercase a power, right?
I see.
Okay.
Does this make sense here?
Yes.
So like so okay, let's I guess use the actual example. So barium sulfate breaks apart. What does it break apart into?
Ba2 plus SO4 2 minus maybe.
Yeah. So now you would do
Okay.
barium 2 plus time concentration times SO4 2 minus. Now it like let's say that there's two of these, right? That's when you take that coefficient and you turned it into the exponent.
Okay.
Mhm.
Cool. I'll send
But
you
here
that. Like, I'll take a picture of the
we have,
bag and then also see maybe
we
there's
have
like even software like in the software or something.
one mole of each.
Screenshot and stuff.
So what we can then do is we can set that equal to, because there should be equal amounts of both of these, right? So we can set each equal to x,
Perfect.
then
Mhm.
x squared is equal to the KSP, and then you can just solve for x that way,
Okay.
right?
Okay.
Uh, but I do want to show you that there's two other things that can happen. So like let's say we have like I'm just gonna make it like AX2 and AX3. So let's say this breaks up into A plus plus 2x minus, and then this breaks up into H plus, I mean sorry, A plus and 3x minus, right? So these would be a little different now. So like this
Sounds good.
would be,
Yeah, no, that makes sense. Yeah. Such a shame I couldn't resolve it like this morning. But like, I mean, that definitely was necessary. Also, I think because there was definitely something in there. But yeah, okay.
oh, can you maybe like mute yourself for
Oh, sorry about that. Sorry. Yeah, 1 second. Sorry, give me 1 second. Sorry.
Yep. Yeah. All right, cool.
Sorry about that. Yeah, sorry about that. Okay.
So yeah, so I kind of like didn't leave myself much room here, so I'm gonna just write this in green. So this will be your x, this will be your 2x, and what you do here actually is x times 2x in parentheses squared, right? And this, what would that give you?
2x squared. Right. Oh no. Oh, sorry. 4x cubed.
Good, 4x cubed. So in this situation, that is what you would set to your KSP. Now, what about this one? This one will be x. This one would be in parentheses 3x cubed. So when you multiply, what would you get?
9x cubed.
Try
Oh no,
again.
no, I'm sorry. 27x cubed. Over here. Yeah, and then
X to the what power?
it cubed. Oh no, this one too. I'm sorry. X to the 27x to the fourth.
Good. So these are the only ones that you'll see. And you'd set that equal to KSP. So those are the three variations here. Now for us, since we have an equal amount of barium and sulfate, we use this one, right? So that's x squared is equal to KSP, which is 1.1 times 10 to the negative 10 power, right? Now, so now we just need to solve for x, right?
Yeah, essentially just take the square root.
Yeah, so how can we take the square root of something like this?
Um, we could break it down like so. If it's 1.1 times 10 to the negative 10th, maybe I know there's some like math trick, right?
So
Like
let's think this right. So like x squared, for it to equal x to the first power, right? So like we're familiar with, the square root symbol and stuff, but like let's think about what does that mean exactly, right? Now let me ask you this first. If I had x to the a power times x to the b power, what would this be? Like what would
Um,
I do with the exponents?
you would add them like
Yep,
x to the a plus x to the b. Yeah,
good. Now, what if I had x to the a divided by x to the b?
that would be x to the a minus b.
Um, x to the a to the b power.
That would be the same, right, as x times a b.
X to the power of ab.
Yeah,
You would multiply them, right?
yeah.
All right, now maybe something can happen like that.
X squared is equal to x to the 1.
Or like what must we do? What can we do to the x squared to get x to the 1?
Um,
Or how about
couldn't it be like x to the 1 times x to the 2, technically? Or, but that would,
so
no,
let
that would be,
so let's try this. X to the a, what can we do to turn it into x to the 1?
make it 0. Oh, no.
So like, let's say so let's say A is some number, right? What can we do to get rid of it essentially?
And turn it into x to the 1, you're saying? Next.
And this stuff that we did here is a hint.
And, okay. Um,
So let's evaluate this one, right? So this one means that, you know, if you add this, would that give you, is it possible for that to give you 1?
yeah, if it's like, yeah, absolutely, yeah.
Oh, like why? Like how?
Like if it was,
Oh, I guess you're thinking if it's like if it's negative or something.
yeah, negative, or if it was like x to the 0 plus 1, maybe.
You said
Like if the a was 0 and the b was 1, or also if it was negative, maybe.
oh, okay. Um so yeah, okay. Let's think about like this and then this. Which one can help you do that? So how about this?
Oh, okay, yeah, I guess this one here, like if because of subtraction, right? Like if it was x to the 4 minus like x to the fourth over x to the 3, and
So,
4 minus 3 is 1.
okay, yeah. I guess let's think about one that will always be the case. Like because like for instance, like here, like if the B was so if the A was a 4 and the B was a 3, then sure, that could give you x to the power of 4 minus 3, which is x to the first power. But can we
Could you also just say x to the a is just 1? That's not what you're getting at, I'm assuming. No.
yeah, yeah. Like
Oh.
could because the this thing over here like can only work if well, it'll only work if A um plus 1 is equal to B, right? Because then you would do if you did A minus B, A minus if B is A plus 1, it'll be A plus 1. And then the a's cancel, and that'll just give you 1. So if you're going to use this, it only will work if a is greater than b by 1. But we want something that will always be true. So why don't we do this, right? Why don't we take x to the a to the power of something? Why don't we use this rule? Where, x to the a is taken to the power of b. That's when you multiply them, right?
Okay.
So here, for instance, I'm going to write it here in red. So x to the a power, x to the a power, and let's just say to the power of x will give us x to the first power. So this means we're going to get what here?
X to the a plus x, like.
So
yeah.
What did we do here?
We multiply. We didn't add. Okay. So x to the ax.
Good.
Okay.
Now,
Because of the parentheses. Okay.
yeah, maybe I shouldn't use x twice like that. So maybe I'll say to the y power. So that could be x to the a times y power is equal to x to the first power. Now, what must y be in order to give you, because we're doing x times y is equal to 1. So we just do a times y is equal to 1 and solve for y, right?
Yeah, but I don't know what a is though either, right? Like these are two unknown variables, or
Yeah, oh yeah, these are just variables, yeah.
um,
So,
so oh, you're asking what a is or y is?
so since we are trying to find out, how to go from, x to the a power to x to the 1 power, what we can do is we can take advantage of this product rule here to get x. So if we then take x to the a power and we take that entire thing and we take it to the y power, that translates into x to the a times y power, and we want it to equal x to the first power. So that could just be then a times y is equal to x. I'm sorry, is equal to 1, right?
Hmm.
And now let's solve for y.
So y would, my instinct would be to be y equals 1 over a.
All right. And why don't we try that, right? X to the a power times 1 over a power. That gives you x to the what power?
Okay. I see it now. Okay.
Yeah. So show me here. So what is this going to turn into?
Oh yeah, so it'd be x to the a over a, which is 1.
Yep. So x to the a times 1 over a gives you the 1, right?
Yeah.
Good. So you see how that always is true, right? Whereas this only was true if that condition was met. Right?
Mhm.
But this is always true. So now to go back to x squared to x to the first power, what must we do to the x squared?
X squared times uh, 1 over 2, or like x squared. Yeah.
Yeah, keep going.
Yeah. Oh yeah. Sorry. X squared times 1 over 2, or like x squared to the 1/2.
To the 1 over 2 power, right?
Yes.
Yep.
Which is like square root essentially. So
Yep. So now that's actually how you do a root, because what they teach us like in whatever middle school or something with like the radical sign over here, that's not going to really uh help us, unless like, the perfect square of something, right? But now we have a way to do that, right? Now, what about this though? What if you had the 4x cubed value, right?
Four, okay, 4x cubed is equal to,
Yeah, let's say let's not worry about the 4. Let's
okay.
just think about the x cubed part. So so essentially the cube root would be like, how would we do that?
3 to the 1 over 3, x to the third times.
1 over 3, right?
Yeah.
There you go. So what if you had x to the 1500 power?
Then uh, x to the 1500 times 1 over 1500.
Exactly. Good, 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 good. So we go back here. So we have our, whoops, x squared is equal to 1.1 times 10 to the negative 10 power, right?
Mhm.
And so let's do, take this to the power of 1/2, right? Now, it could be a little confusing because I wrote with E notation, but let's say I wrote it like 1.1 times 10. Oh, yeah, times 10 to the negative 10 power. If you take this to the power of 1/2, right? Let's not worry about the 1.1 now, but the 10 to the power of negative 10 would turn into what?
Uh, -5.
Exactly. Um, and for the 1.1 thing, like we know that the square root of 1 is 1. We know the square root of 2. Well, I guess we don't know that, but I do. It's 1.4. But yeah, you can kind of just move on to square root of 4, which is 2. So we know that 1.1 must be, between 1 and 2, but significantly closer to 1. So we could just say that that's a 1. And so that'll be your answer, right?
Oh, yeah. Okay.
Because, yeah, like first of all, it's the only one that has the 10 to the negative 5 power,
Uh-huh.
but also we know that the 1.1, square root of 1.1 is going to be pretty close to 1.
And so, like, I guess,
So why
like,
didn't we do that?
this is I guess just something to expect with double AMC question. I mean, obviously,
Oh,
this is
you mean
Jack
why are they
Weston, but
giving us that answer?
they
That
just throw us, they
Yeah,
could throw us
yeah,
information that's not to be utilized. Okay. Okay.
yep, yep, yeah,
Okay.
yeah, yeah. You're gonna, yeah, expect to see that kind of thing, because again, like this is a test made for pre-meds, and pre-meds are the most thorough, like hardworking, perfectionistic people ever, right? So it's very, very hard for a pre-med person to not to like ignore something, right? So if you want to design a test to really test pre-meds, um, you can take advantage of the pre-med's natural inclination to think that everything matters. Uh, so that's why this is given to us here. Because two things. One, even if we needed the molar mass of barium sulfate, you're supposed to know how to find that out from the periodic table, right? So you ultimately don't need it anyway. Like, sorry, even if you needed it, it's not something that you need for them to like just straight up give you like this because you can just figure it out from the periodic table, right? So that's one thing. The other thing is just because they're giving it to us doesn't mean that we need to use it. And so uh so expect to see that. Expect to see like red herrings and extra information that uh is meant to like maybe psych you out or something. Uh, but we're just going to use the information that we need. Yeah.
Got it. Makes sense.
Mhm.
17.
Okay, so let's talk about the different definitions of bases. Okay, there's the Arrhenius one, Bronsted-Lowry one, Lewis one. Okay, now the Arrhenius one, so and then I'll write acid and base. So the Arrhenius acid is so the Arrhenius definition is like the most simplistic, and an Arrhenius acid is just something that produces hydronium ion.
And this is in the context of water. Is that something specific to Arrhenius or?
Good point, good point. So yes. So remember how I mentioned previously the KW?
Uh-huh.
So like interestingly enough, right? Like people like in middle school or whatever, elementary school or something, we learn about acids and bases on a pH scale of like 1 to 14, right? Um, but now we know that okay, so where does that come from, right? It comes from the auto ionization of water, where water can so one of these water molecules will donate a proton, and the one that gets the donated proton will be hydronium, and the one that loses the proton would just be the hydroxide ion. And so the Kw of the water is, well, like essentially like the concentration of that. So that's going to be like 1e negative 14. And
What
then
does W stand for?
water.
Oh, water. Okay, okay, got
Yep.
it.
So so that would mean that, this would be, you know, both of these would be times 10 to the negative 7. So that's where like that pH scale comes from the autoionization of water. Now, later on in like college, you learn about pKa, right? Because you've noticed like how we mostly talk about pKa now and not pH. Um, and that's because pKa is actually that intrinsic factor that makes something, an acid or a base, rather than it being related to something, in water. And you'll see that strong acids actually have pKa's of like negative values, like well below the one of the 1 to 14 scale, right? And, strong bases would have pKa's of like 30 or 40 or something way above the 14 mark. But yeah, the Arrhenius one definition is based on the autoionization of water, which is why you see that, yeah, so the Arrhenius acid is the hydronium here. The Arrhenius base is the hydroxide. So in other words, an Arrhenius acid is defined by producing hydronium ions, and an Arrhenius base is defined as producing hydroxide ions. Okay, so that's that. And that's like the most rudimentary definition that they'll talk about the least. Next up, Bronsted-Lowry. And this is the most likely definition of acid that they'll use. Like when they say acid bases, they're going to imply the Bronsted-Lowry definition. So that's where the Bronsted-Lowry acid is a proton donor, and the Bronsted-Lowry base is a proton acceptor. Okay. So if a passage or a question just says acid or base, that implies acid is the proton donor, and then the base is the proton acceptor.
This feels more like pH scale, like that's what as opposed to pKa or
Oh no. So the pH thing was just me kind of
okay.
like how that's from the autoionization of water, but um, but so should I put this? So like so let's say, okay, so let's for water, right? Um, if you add a Bronsted-Lowry acid to it, the Bronsted-Lowry acid would donate a proton to the water to give you hydronium, right? Right? And the um Bronsted-Lowry, so same thing with the water, but if you added the Bronsted-Lowry base, right, it would the Bronsted-Lowry base would accept a proton, and that proton will come from the H2O, so that's going to create the OH minus, right? So like if you took water, you expose it to a Bronsted-Lowry acid, the Bronsted-Lowry acid would donate a proton to the water to give you hydronium. The Bronsted-Lowry base would accept a proton from water, which means the water loses a proton and that'll give you the OH minus. And those are what these things are, right? But so all Arrhenius acids and bases are Bronsted-Lowry acids and bases, but not all Bronsted-Lowry acid and bases are Arrhenius ones. So what I mean by that is, uh, so for instance, a carboxylic acid like this, right? This would lose its proton to give you this plus this, right? Are you familiar with that? Like,
What's the
oh,
like this reaction?
yeah. Mhm.
Oh, yes, this is the carboxylic acid, right?
And then that's so it's going to behave as this Bronsted-Lowry acid, so it's going to donate a proton, right? So
Yeah.
it deprotonated, right?
Yes.
And so so like usually we draw like an H plus, but like technically that you're not going to have like just protons moving around and on their own, right? So while we might write H plus, it's really, if this is aqueous, right? It's really the H plus that goes to water to create H3O plus, right? And so that shows you that this is a Bronsted-Lowry acid because it donates a proton, and it just so happens to donate protons to water because if you mix it in water, right? So it's going to produce this hydronium ion. So this is an example of how a Bronsted-Lowry acid can also be classified as an Arrhenius acid. But what if we had something else, right? Like for instance, like well, ammonia, right? That can produce something like, you know, NH, like if we added, like whatever, an acid to it, Bronsted-Lowry acid, right? Um, the Bronsted-Lowry acid will donate a proton to the ammonia, which would then create the ammonium molecule here, right?
Okay, so, uh, so is this now the Bronson-Lowry acid here?
Oh, so the Bronsted-Lowry acid, I mean, I didn't draw
Oh,
it, but I just wrote it. And it's defined as donating a proton, and here the
oh,
Bronze,
that's right. I'm sorry. Sorry,
yeah.
I got confused.
This would be the Bronsted-Lowry base because it's accepting a proton, and it produces this ammonium ion, right? So now this is an example of a Bronsted-Lowry acid that is not an Arrhenius acid because we're not creating hydronium this time. We're creating ammonium. Okay. So like you can kind of think of it like this. Like this circle includes all of the Arrhenius acids. This circle, whoops, includes all of the Bronsted-Lowry acids, and you can see that all of the Arrhenius acids and bases are within the are a subset of the larger set of Bronsted-Lowry stuff. So you can have so every Arrhenius acid or base will be a Bronsted-Lowry acid or base, but not every Bronsted-Lowry acid or base will be an Arrhenius acid or base. So, so yeah, this will make more sense like as we kind of move on, but so the Bronsted-Lowry definition of acid and bases will be the default if they ask you about acid and bases. Lewis acids and bases are a bit different. So Lewis acid would be an electron pair acceptor. Yep. And a Lewis base is an electron pair donor. And this is going to be more relevant in organic chemistry because the electron pair acceptor, aka the Lewis acid, is the electrophile, right? And the electron pair donor is the nucleophile. Okay. And so examples of these could be, so I always say the most common nucleophile is a a hydroxyl group because it has these lone pairs, right? And then the most common electrophile would be a carbonyl group, like a carbon double bonded to an oxygen. And so what happens is the the carbonyl carbon is partial positive, oxygen partial negative. So this is going to attack this, meaning it's going to donate an electron pair to it, right? And so now this is like an alcohol here. So let's just call it like, ROH. Now this is an example of a Lewis base, right? That does not accept protons. Okay? So just like every Arrhenius acid or base will still be a Bronsted-Lowry acid or base, but not the other way around. Same thing for Lewis. Meaning Bronsted-Lowry and Arrhenius acids and bases must still be Lewis acids and bases, but there could be Lewis acids and bases that are not Bronsted-Lowry or Arrhenius acids and bases. So mostly important thing is just that Arrhenius is acid is just anything that produces hydronium, an Arrhenius base, anything that produces hydroxide. And then Bronsted-Lowry acid is a proton donor, Bronsted-Lowry base, proton acceptor. And that's the default definition of acids and bases when they talk about acids and bases. But if we're talking about nucleophiles and electrophiles, that's typically in Orgo. That's where the Lewis definitions come in.
Got it. Not to go on a tangent, but would this be a SN2 reaction, like one step kind of thing?
Yep.
Okay.
Because yeah, it'll make a bond with this, momentarily moving these electrons from the double bond to the oxygen. And so the intermediate is going to look like this, right? Oh, this will be a plus here. And then when this comes back to reform the double bond, it'll kick off that leaving group. Okay. But yeah, any questions about these?
Yeah, I think I just have to be careful because
Hmm.
like Bronsted-Lowry acid is a H plus donor, right? But then when you jump to
Hmm.
Lewis base, Lewis base, it's an electron pair donor. So that kind of I just have to
Yeah, so you can think of it
yeah.
like this, right? Acid donates positive charged things, right? And base accepts positively charged things, in these examples. But here you can see that the acid can produce positive things and the base can produce negative things. And that's more kind of similar to this because the electrons have negative charges, right? So something that accepts a base will accept a positive charge like a proton. Um, but it can't accept negative charges, right? Because, in terms of like opposites attract, right? Like you're either gonna be attracted to a positive or a negative, but not both. So that's why, a base can accept a positive and donate a negative. Because let's say it didn't accept a positive. When it donates its electron pair, it gives away the electrons, becoming positive itself, right? Like here. So that's why so the base will just want to be positive, and it can be positive by either accepting a positive charge, like a proton, or by removing negative charges, like electrons, right? And then
Yeah.
an acid would donate a positive charge, meaning it gives away a positive charge, turning negative, right? Um, and if it didn't give away a positive charge, how else could it be negative? If something gave it electrons, right? So that could be a way of thinking about that. So yeah, where you're, uh, what do you think?
That make, that makes sense.
Okay, so yeah, so for this one, you chose NH3, right? And the NH3, well, Arrhenius base is something that produces hydroxide. NH3 would not produce hydroxide, right? Um, because it'll just, if you put it in with water, I mean, NH3 it could act so like okay, if you put it in with an acid, it'll act as a base. So the NH3 would get protonated and it'll be NH4. I drew that a little earlier. Uh, but it can also act because NH3 has a lone pair. It can also act as a nucleophile. So NH3 can be a Lewis base, right? It could be a Bronsted-Lowry base as well, but it can't be an Arrhenius base because it does not produce hydroxide. But KOH, that just dissociates into K plus and OH minus, and that's what an Arrhenius base does. So yeah, that's why it'll be D.
Yeah.
Mhm.
39.
Okay.
I was gonna set up a proportionality, but it
Oh,
seems like
uh, yeah.
what's that? Oh yeah, it seems like just a simple proportionality. I don't know why I got it wrong.
Well, proportionalities could work either if something's proportional or something that's inversely proportional. So we need to be aware of that relationship first. But we're dealing with gases here, and we're dealing with so think about what you're being given. We're given let's say an initial pressure here, an initial temperature here, um a second, final temperature there, and the second or final pressure is what we need to find, right? So now we must think about how are these, so the proportionality between pressure and temperature, right? Because if they're proportional, then you can make the proport. So I'm guessing what you did was something like, let's say 1.5 ATM over 320 is equal to X over
Yeah.
450, right?
Yeah, exactly.
So that's going to be, so any equation come into mind when you see these values?
No, I mean initially I thought PV equals nRT, but
Yeah.
obviously that's
Yep.
not. Oh,
Yeah.
okay.
Yeah. Yep. So,
Oh,
mhm. So PV equals nRT, right? So we see that so we want to see the proportionality between pressure and temperature. Because the thing is, like, nothing else is changing here. So like whatever the n is doesn't change. So we don't have to worry about that. The volume also doesn't change, so we don't have to worry about that. And R, which is the ideal gas law constant, obviously doesn't change. It's a constant. So we can really just write pressure is proportional to temperature, right? So, um, so what that means is that yes, uh, if pressure increases, temperature increases, or if temperature increases, pressure increases, right?
yeah.
So it seems like so the temperature is increasing, right?
So that pressure should increase too.
Yep. So right away we can get rid of A because that's a lower pressure than 1.5 ATM, right?
Yeah.
All right. Now P. So you know what? You might be able to. Oh, you know what? Okay, okay. So so writing it out like this. So this is basically like okay, P over. So let's say P1 over T1 is equal to P2 over T2. Um, so let's see. P1, wait, okay. This proportion should then, let's see.
How did I get 4.2?
This should work then, the proportion.
Did I?
So yeah, so let's see. So I always like to write it out algebraically first. So this would just be multiplying T2 on both sides. So P1 times T2 over T1 is equal to P2. So that's P1 1.5 ATM, T2 450 Kelvin divided by
Yeah.
T1
I
320.
just did it by calculator and I got 2.1. I'm not sure why.
Oh,
Okay.
wait, but you can't use the
Oh,
calculator.
yeah, that's true. Yeah, 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 that's true.
So throw that somewhere else.
All right.
Um, let's talk about how we can do the math here. Um,
So I would cancel the zeros, maybe.
all right, good, yep.
And then I know 45 times 2 is 90. So 45 times 1.5 would be 60.
So
Yeah.
you do. So I think what I would do here is then I would try to factor. So like I would be like, okay, um, like a common multiple or something between the 45 and the 32. So I'm going to treat the 32 as a 30, and 5 goes into 36 times. 5 goes into um 45 9 times. Oh, that's even, and then 3 goes into 6 twice, 3 goes into 9 3 times, right?
Uh-huh.
And then the 1.5, I like fractions, you don't have to do it this way, but fractions mean that you don't have to round. So like 1.5, I would write as 3 over 2. So it's 3 over 2 times 3 over 2, right? Um, so, well, I could also write it like 3 over 2 times, wait a sec. Let's see. Okay, let me go back. Oops. So, okay, so this will just be 9 over 2 over 2, which is the same thing as multiplying it by its reciprocal, 1 over 2, 9 over 4. But okay, let's do it without the fraction. So 1.5 here times 3. Well, that's not bad, right? Right? That'll just be 4.5, right?
Uh-huh.
1.5 times 3, right?
So 1.5 times 2 is 3. So then 1.5 times 3. Yeah.
Yep. And I'm also thinking of like 15 times 3, right?
Mhm.
So 4.5 and then divided by 2, right? So, 4 divided by 2 is 2. 4.5 divided by 2 will be a little higher than 2. So, yeah, this proportion, uh, works here. Um, but, still start with this because what if they said, what if instead of temperature, they gave us volume, right? Because, pressure is proportional to temperature, but pressure is inversely proportional to volume, right? So if they gave you volume values, then this proportion wouldn't work, right? You would have to do pressure 1 times volume 1 is equal to pressure 2 times volume 2. That's if they're inversely proportional. Okay. So for this question, you start off with the ideal gas law to identify the proportionality between the values that they give us. And they give us P1. So they give us pressure and temperature, and we know from ideal gas law that pressure is proportional to temperature, and that means you can just do this nice proportion here. But if they had given you pressure and volume, pressure has an inverse proportion to volume, and you won't be able to do this type of proportion. It would have to be this type. But okay, but you did it this way, so maybe what you did was you forgot to do the divide by 2, and you left the 4.5 because you chose 4.2.
Possibly. Yeah. That's possible. Yeah. I mean, in the future, I probably wouldn't ask you about this question just
Okay.
to make more use of my time. But yeah. But sorry. But okay. Yeah, that makes sense then. 43. Okay. Tip to tail and like adding, subtracting scalars and vectors.
So yeah, so I think it's best to think about it because you're always going to do a vector addition, but if you make the direction of the vector opposite, it'll it'll be a negative vector. So like here they're saying P minus Q, so I take that to mean P plus negative Q. And so they give us P here, and they give us Q here, regular Q. So if I make this regular Q go in its opposite direction, this is now negative Q.
Okay.
Okay. And then you can do your tip to tail. So that would be like this, right? For the negative Q. And your resultant would be that, right?
Okay. Okay. That's easy. Okay.
Mm-hmm.
Oh, wait, is that? Okay, yeah, 43. Sorry. Yeah, 43.
Okay. So, okay. So they're giving us, yeah, for calculation problems, you want to maybe you start off by taking an inventory of what values they give you, and then you can kind of figure out things from there. So the speed here is 360 kilometers per hour. Okay. And here is time, right? Um, and okay, and they're asking for acceleration. So okay, we have time, we have a velocity. Okay, what's the formula for acceleration?
Is it delta V over delta T?
Exactly. Change in velocity over change in time is acceleration, right? Right.
Yeah. Yeah.
Okay. So we have, and the delta V is just like V final versus minus V initial, right?
Yes.
So this V final here or V initial here?
That's fine.
Good. What's V initial?
0.
Yep, because
Because it starts from rest.
excellent. Good. So that's basically going to be 360. So we're going to do some dimensional analysis here. So what I like to do is like, so if I'm given kilometers, right? Like I'm going to already tack on the times 10 to the negative 3 so I can turn it into just meters. So this is times 10 to the negative 3 meters per hour, right? And then I'm going to convert it, convert the hours into seconds. So up here, 1 hour is, you could do like 60 minutes and then you could do another thing. Um, so I'll do it that way. So 1 hour is 60 minutes, and then 1 minute is 60 seconds, right? And then this would give us our oh yeah. I used M for meters, so I'm gonna write MIN for minutes. But this would then give us uh of something that will have the units be meters per second, right? So because you cancel out the hours here and the minutes here, so you're left with meters over seconds. So yeah, let's do this. So basically, um, I mean, we could do like the 60 times the 60 is 3600. Um, and then I can just do like, I'm gonna kind of move this around, like move this here. So we have 360 times 10 to the negative 3 meters over 300, like 3600 seconds, right? Now, these values are pretty much the same. They're kind of like off by, like an order of magnitude. So we can do a couple of things. We can turn the thing on the top, into, there's a lot of things we could do. I mean, we can say, 6 goes into, let's do it that way then. So 6 goes into 360, 60 times, right? Right. Like, uh, 360 divided by 6, right? 6 goes into 36 6 times, and there's a 0 on top.
Yeah. Yeah.
And then I'll do the same thing for the bottom. 6 goes into 3600, 100, right? 600 times, right? like 3600 over 6. 6 goes into 36 6 times, and then there's 2 zeros.
Mhm.
Right? So now this is 60 times 10 to the negative 3 divided by 600, times 10 to the 0. So now I can get rid of these zeros, and then 6 goes into 6 once, 6 goes into 60 10 times. So this is 1 over 10 times 10 to the negative 3 power. So that's 0.1 times 10 to the negative 3 power, which is, we can say 1 times left add, right subtract, negative 4 meters per second. So that can be our, wait, let me make sure I did this right here. 360. Oh, crap. I made a mistake. So 360 kilometers. So kilometers is larger than meters. So this should be 360 times 10 to the third power, not times 10 to the negative third power.
Oh, okay.
Yeah, my bad. This is positive that, positive that, positive that, positive. Whoops. Positive that, and I'm going to just move this. So 0.1, 1, 2, 3. So that's 100 meters per second as your V final, right?
Yeah. And then just over.
Over the 50, right? So over the 50 seconds, get rid of the zeros, and then 5 goes into that twice, right? So there you go. So I think what happened with you was, because, the answer that we got was 2, but I think you maybe had the 2 as the denominator, which would have given you 1 over 2 rather than 2 over 1. And I think that's how you got the 0.5.
Okay. Yeah.
Yeah. But yeah, pretty much, that's yeah.
Um, 6. Okay.
Uh, so okay, so let's do this. Let's think about this conceptually first. So for instance, you know, our balloon here, and then like on the left side, it's open to the atmosphere, right? So let's say that the levels of the water, or I guess mercury in this case, are equal, right? And then let's say like this vector here is pressure of the balloon. And this vector here, I'm just going to write pressure L, meaning left. Okay. So if these levels are equal, the same, um, the pressure of the balloon should be equal to the pressure on the left side, right?
Yes.
All right. Now, if the pressure of the balloon was larger than the pressure on the left, what do you think would happen with the levels of the mercury here?
This side would increase. The pressure of the left would,
Yep,
the mercury would go higher.
yep, exactly. Good. Now, in this question, the left side is lower, right? So what must that mean in terms of,
The
that?
atmospheric pressure is greater.
So so um so I'm just making it like pressure on the left side, uh not anything with the atmospheric pressure yet. So, but yeah,
No.
pressure on the left side would be greater than uh pressure of the balloon, right? Okay. Now, sure, this outside part is exposed to the atmosphere, so there is an atmospheric pressure that's pushing down on it, right? Um, and since they are asking for the pressure of the air inside of the balloon, right? We can say that the pressure on the inside of the balloon is going to be, well, okay, how about this? Okay. So the pressure of the balloon should be less than the atmospheric pressure, right?
Pressure of the balloon should be correct. Correct. Yes.
And what is atmospheric pressure?
Uh, they gave it to us at 1 times 10 to the fifth pascals.
All right. And since the choices are in kilopascals, what would this value be in kilopascals?
So 1 times 10 to the fifth times 1 Pascal. There's 1 times 10 to the third pascals and 1 kilopascal. So 10 to the fifth, 5 minus 3 essentially. So 10 to the second kilopascals.
Yep,
Yeah.
like 100 kilopascals, right?
Yeah.
So what can we eliminate?
A and B. Wait, okay, so it's asking what the pressure in the balloon is, correct? Yeah, what is the pressure of the balloon? So if it was hot, if it was okay, exactly, yeah. So A and B, because if it was higher, then this would be
Mhm.
going up. Okay, yeah, I see what you're saying.
Good. So right away we can get rid of A and B. Um, and it's interesting because 49% chose B, right? 11%, so 60% chose those. So, but right away we can get rid of those. So now we want to see, is it this or this, right?
Correct.
So now this is why I didn't want to just make the pressure on the left equal to the atmospheric pressure, because there's the gauge pressure. I'm going to use green, which is like, let's say P something is equal to P ATM plus rho GH. Are you familiar with this formula here?
PGH. I might have seen it on my Anki, but it's been a minute. So
Yep. So this is like, it could be called gauge pressure, but it essentially is the sum of the atmospheric pressure, and this value here could be different things in different contexts. Like let's say for instance we had some vessel of water or something, right? And let's say some ball is floating on top of the water, right? It's going to experience, since it's exposed to the atmosphere, an atmospheric pressure, right? Okay. Now, same thing, but now let's say the ball is submerged a distance of h, right?
Mhm.
So now this ball it still experiences the atmospheric pressure, but it also experiences the pressure of the water on top of it, which we can express as rho GH, rho being the density of that water or fluid, G being, the gravitational field strength or the, gravity, H being how deep it is, right? So that now, so this is it being applied to like being submerged, let's say. Um, but here in this case, we don't have like, an object submerged in water or mercury or anything like that, right? But we do
So
have,
Sorry for this one, Shane. So
Yep.
I guess but I get confused and I'm thinking buoyancy, but this buoyancy doesn't come into play with this, right? Or I guess it's just situation dependent, depending on the object being submerged. Or
No, no, no. There's definitely a buoyancy, right? But this is just if we wanted to figure out the pressure of something submerged,
okay,
right?
yeah,
Um, but yeah, buoyancy would be some type of force that is going to be opposing the direction of gravity. Um, but yeah, for this one, we're just, and that's a type of force, yeah.
okay.
Uh,
Sorry about that. Yeah.
no, 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 you're good. So, yeah, okay, now in this manometer example, it's very different, right? It's like we don't have something submerged or anything like that, but we still do have something like this, and that's this water column here. And they're giving us H, so that can be like a hint here that we're going to be using this formula with this, right? So now let's just think about it like this, right? Like this equation, right? Um, you know, so in this example here, where the levels are equal, like the height here you see is really the difference between the left bottom and the right top, right? Right? Like if this came up to here, right? And they're equal levels, this H value would be zero. Like it won't be a thing, right? And then it'll just be that and then that means this will turn into a zero. And so that just means that the pressure on the left is atmospheric pressure and the pressure on the right, pressure from the balloon, is also atmospheric pressure. That's this scenario here, right? But this scenario here, right, has so let's say this, is H. The pressure of the balloon here is going to be atmospheric, pressure plus the, this water column here, rho GH. Whereas on the left, it'll be atmospheric pressure minus rho GH. So now here, let me get rid of this. So here, it's like this. It's like, okay, we know that the pressure on the left is greater than the pressure on the right, but by how much is it greater, right? And it's going to be by rho GH, by that much. Okay? So that's what this means. So we know that the pressure of the balloon is now going to be equal to, the pressure of the atmosphere minus rho GH, because the pressure on the left is going to be the pressure of the atmosphere plus rho GH, right? So we can agree that the pressure of the balloon is smaller than the atmospheric pressure, and it's also smaller than the pressure on the left, right? What are you thinking?
No, that makes sense. That makes sense.
Mhm.
Yeah,
And
and
so,
the equation makes sense to me also because
yeah,
it's
yeah.
asking, and then that lines up.
Yep,
Nice. Yeah.
yep. So it's like this. It's like we know that the pressure on the left is greater than the pressure on the right, but then the question is by how much is it greater? And it's greater by rho GH, that much. So rho, they're telling us, is 14,000, kilograms per cubic meter. And then G, we can use, this value here, 10 newtons per kilograms. I mean, there's also 10 meters per second squared, and it's the same exact thing, but it's more useful to use newtons per kilogram because that way we get to eliminate the kilogram part. And then H, which is 50 centimeters, which is just 0.5 meters, right? Plus the 101 or 100 kilopascals, right? Oh, sorry. It would be the
You're right.
100 kilopascals minus that because it's this, right?
Oh, that's right. Kilopascals is pressure. Okay.
Yep. So now what I would do is I would take, okay, 0.5 is just 1/2. So I'm going to just say, okay, that goes into 14,000, 7,000 times, right? And then it would be 7,000 times 10, which would give me 70,000. But this is all, oh, so I should say this. This is important because we cancel these out, and so we get newtons. Oh, and then this meter cancels out with meters cubed. So this on the bottom is meters squared. Okay. So we get as our answer here 70,000 newtons over square meters. Okay. Now, pressure is force over area, and force is measured in newtons, and area is measured in square meters. And so this is a Pascal. A Pascal is the same thing as newtons over square meters. Okay? So this 70,000 Newton per square meters is the same as 70,000 pascals, right? Now, we want it to be in kilopascals. So this would be how many kilopascals?
Would be 70? No, 700 kilopascals, right?
So,
Seven, oh,
so 1,000 pascals,
oh, you're right. 70 kilopascals. Yeah, sorry.
yep, kilopascals. And so now it's the 100 kilopascals of the atmosphere minus 70 pascals, which will give us the 30. Okay. Now,
Got it.
we could have messed this up a little bit. Like, let's say that I forgot to multiply this 10, right? And that would leave me with 7,000, you know, rather than 70,000. So that would be 7,000 pascals, which would be 7 kilopascals, right? And a 100 kilopascals minus 7 kilopascals would give us what?
93. So,
Yeah.
so you think AMC would do that? Or, oh, yeah, I guess they would. Yeah.
And you see how, so right away, conceptually seeing this, because the thing is, most people who are taking the MCAT and stuff were like bio majors, and bio, they don't really explain why things happen. They just say this is what happens. So pre-meds who are used when they take the physics classes, like, I don't know if this was like it for you, but like they usually hold their calculator and they read the question and they just plug and chug, right? But like, you can't do that on the MCAT because you don't have a calculator. But at the same time, the questions on the MCAT won't be simple plug and chug. And if you're looking at this and thinking, okay, I have this, I have height, I have pressure of the atmosphere, I have density of the mercury, what equation do I use? That's not going to be sufficient. You want to first be able to understand what's happening conceptually, and so conceptually, before we even read, those, or before we did any numbers or math, right? We were able to determine that the pressure of the balloon is smaller than the atmospheric pressure, and that enabled us to get rid of A and B, which is already 60% of 60% of people chose that. So right away, you're doing better than 60% of people, right? And then you see that it's a very easy mistake to end up getting 7 kilopascals, and that's why 21%, more than a fifth, chose C, right? But we, did it right? And that got us 70 kilopascals, and then that gets us 30 kilopascals. But you see how, only 19% shows that. So, uh, yeah. So this is a good question to see the benefits of conceptually understanding it. Because, like, if you don't have time, right? At least conceptually understanding it would bring you to 50-50, right? But then I just wanted you to see that in between C and D, where the choices are really similar. I don't want you to just be like to just see how D is the answer. That's why I showed you if we forgot to do the 10 here, we would have gotten C as our answer because 170, 107. So this is a good question because it tests a lot of things. Yeah.
In the double AMC, they might also put instead of C, they might put 300 kilopascals or 3 kilopascals, right? That's certainly up for game two, right? Or
When you say that, what do you mean?
in the answer choices, they might put like 300 kilopascals, 3 kilopascals, zero point 0.3, or they might try to get you with a like off by zero or off by like a decimal kind of thing. I don't know. Sometimes.
Oh, well, I mean, in this question, we're subtracting it from 100 kilopascals. So
Mhm.
we know that, I mean, if it was 300 kilopascals, we know that can't be the answer because
Oh yeah.
we would have negative, like 100 minus 300 would be negative 200, and we can't have negative pressure.
Okay. True.
But I
True.
think I know what you're saying. Like, yeah,
Yeah.
there
Like,
the other answer choices are not going to be like completely out of left field, you know?
okay.
They'll have some type of logical basis behind them. Um, but yeah.
Makes sense. Oh, that was a good one. Yeah.
Yep, yep. So yeah, I think we're
Okay.
about done here. But yeah, this was a really good one. And yeah, so you want to basically be able to see things conceptually and then be able to use the formulas and the knowledge that you have to, kind of work from that. Because I mean, another thing here is like we had to know that newtons per square meter is a Pascal because they didn't tell us, right?
Okay.
So
Yes.
there's that. But but yeah, I think for the most part, we went over some really good like math stuff, like how to do square roots and cube roots and any of that stuff. Um, and a lot of this conceptual stuff. So yeah, I would say so. Yeah, continue to review these content diagnostics, and once we finish reviewing it, we can have you start that section bank.
Okay. Okay. So I guess for next session, I can make it a little bit more effective and go through them all, and then you're saying filter the ones that even after seeing the explanation that I don't understand, right?
Yep.
Is that okay? Okay.
Yeah.
Got it.
And it could
Makes
even be
sense.
like if you did understand one, but you just wanted to see how I would approach it, that can be something too.
Okay.
Yep. So should I put you in for next Thursday?
I'm gonna go on my I have your Calendly.
Oh
So
yeah.
what I'll do is
Yep.
I'll schedule one just based on my schedule here in the next like
That
hour
works.
or so.
Awesome.
Yeah.
So yeah, and it should be 150. Wait, let me make sure. Oh no, 1.5 hours, 113.
Just let me know if you got that.
Oh, okay. Yep, I got it.
Perfect. So yeah, I'll go on and then find the next appointment.
Awesome. And how's cars going?
Yeah, I looked at your thing, and so
Mhm.
just kind of
Yep.
still need to do some work, but
Mhm.
um,
Got it.
and I need to start doing some more practice passages and stuff like that. But yeah, like you said, slow, speed is fast.
Awesome. All right. Cool. Yeah. Keep up the good work, and yep, I'll see you sometime next week. All right. Take
Okay,
care.
thanks. Okay.